Hey everyone, this video is to talk about dependent events. So dependent events are two or more events, just like independent, they're happening one after another. The probability that one occurs does affect the probability of the other occurring. That's why they're called dependent, because they depend on one another. So your formal formula of this is the probability of A and B happening is the probability of A times the probability of B given A. Remember this, probability of B given A is the probability of A intersect B over the probability of A. I will be the first one to tell you that I absolutely hate this formula. I don't think it's very intuitive, so I'm going to teach you how to think it through instead of using this because I think this formula is very, very challenging. So just like we did with independent events, we're always going to assume that the first event occurs. This time we're going to see the words without replacement. That means if you're reaching in and picking something out or you're choosing something, you are no longer keeping it in there, so you're changing the denominator and potentially the numerator of the next event. So the first example, we did this one in the independent, same kind of scenario. A jar contains 3 red, 5 green, 2 blue, and 6 yellow marbles. That means that I have a total of 16 marbles. A marble is chosen at random from the jar. A second marble is chosen without replacing the first one. What is the probability of choosing a green and a yellow marble? So here's what we do this time. I start it the same way. Probability of green times the probability of yellow. Looking at my sample space right now, I have 16 marbles. Of those 16 marbles, 5 of them are green. We're going to assume that it happens, that I reach into the marble and that I pick out one green marble, which means in my sample space over here, I'm going to get rid of one of the green marbles because I've chosen that and I've kept it outside of the bag. Well, now that means my total changes from 16 to 15. So my denominator is going to decrease by 1. Of those 15 marbles, how many are yellow? 6 of them. Now, you can go ahead and you can multiply these across like you normally would, or remember, you can simplify fractions. You're allowed to cancel something in the numerator with something in the denominator. That means that even though 5 over 16 doesn't reduce, they don't have common factors, and 6 and 15 don't reduce, that I can reduce 5 and 15 because they're both divisible by 5. So 5 divided by 5 is 1. 15 divided by 5 is 3. And then I can do the same thing with 6 and 16. Both are divisible by 2. So 6 divided by 2 is 3. 16 divided by 2 is 8. So that's going to give me a fraction of 1 over 8 times 3 over 3, which actually, what you should notice, 3 over 3 is equivalent to 1. That's 1 over 8 times 1, or just 1 over 8. You are totally fine to multiply 5 by 6 and get 30, and then do 16 and 15 to get 240, but you're still going to have to reduce in the end, so you want to make sure that you reduce early and often if possible. Alright, so for our next example, a card game is being played where players want to draw 2 face cards in a row without replacement. What is the probability of drawing 2 face cards? That's the probability of drawing a face times the probability of drawing a face. So looking at my sample space right now, I currently have 52 possibilities. Of those 52, 12 of them are face cards. So I reach in to my deck of cards. I pull a card out. We're going to assume that it happens, and it's a face card. I take that face card and I place it to the side, which means let's assume that I grabbed the King of Clubs. It's no longer there. That means when I reach in again, I no longer have 52 cards, but now I have 51 cards. And of these 51 cards, remember, the King of Clubs has been eliminated. I've taken it out of the pile. That means that I no longer have 12 face cards. I now have 11 face cards. Reducing where I can, I know that 12 over 52 is 3 over 13. And then 11 over 51 won't reduce. What I could do, however, is I know 51 is divisible by 3. 3 divided by 3 is 1. 51 divided by 3 is going to give me 17. And now you have all prime numbers, which means none of those will reduce. So in the numerator, 1 times 11 gives me 11. And 17 times 13 gives me 221. Final answer. All right, for our last example, we're going to go back to the jar example. So a jar contains 3 red, 5 green, 2 blue, and 6 yellow marbles. Just like before, I have a total of 16. A marble is chosen at random from the jar. A second marble is chosen without replacing the first one. Without replacing means right away these are dependent events. What is the probability of choosing 2 red marbles? That's the probability of red times the probability of red. So once again, we're going to assume that the first event happens. So I reach in to my bag of marbles. I have 16 of them. 3 are red. I pull that marble out. I look at it. I'm assuming it happens, which means I look down at the marble and I see that it's red. I take the red marble and I put it to the side. That means 1 red marble has gone away. My new total is now 15. Of those 15 marbles, 2 of them are now red. We're going to simplify where we can. 3 over 16 doesn't reduce, and neither does 2 over 15, but remember, you can cross out any numerator number with any denominator number. So 3 divided by 3 is 1. 15 divided by 3 is 5. 2 divided by 2 is 1. 16 divided by 2 is 8. So I'm going to have 1 over 8 times 1 over 5, which is 1 over 40.